Okay folks, we are going to look in this video clip at some language that we use in graph theory and also some concepts that we're going to use in graph theory. The first thing I want to look at is the notion of a subgraph, and that's going to become important later on when we look at trees and spanning trees and that type of thing, and connected graphs, etc., and bridges. Those are all things that are still coming. So we're still learning the language. Okay, so let's see what it says. What is a subgraph? Well, we say, and look at the notation here, G prime is a subgraph of G. So we're going to write it as G prime. So G prime, which has a vertex set V prime and an edge set E prime, is called a subgraph of G with a vertex set V and an edge set E. We write this as G prime is a subgraph or subset of G. Now in set theory we've started using these symbols. That was, I think, in chapter 0 that we worked through. Okay, so we're using the same symbols to denote the very same idea, which is called a subgraph. So this will be the case. G prime will be a subgraph of G, provided that the vertex set of G prime is a subset of the vertex set of V, and the edge set of G prime is a subset of the edge set of G. Now he delves deeper into this definition. He says, we say that excuse me, G prime, which can be written as that, is an induced subgraph of G, provided that the vertices in G prime is a subset of the vertices in V, so vertices V in G, and every edge in E, in other words in the original graph, whose vertices are still in V prime, okay, is also an edge in E prime. Okay, so again, let's read that again. It's an induced subgraph if the vertex set of G prime is a subset of the vertex set of G, and every edge in G whose vertices are still in the vertex set for G prime is also an edge in E prime. Now that seems a little bit complicated, but let's see what it means. So notice that every induced graph is also an ordinary subgraph, but it doesn't work in reverse. We can think of a subgraph as a result of deleting some vertices or edges from the larger graph, from the original graph. Okay? So for the subgraph to be an induced graph, we can still delete vertices, but now we only delete those edges that included the deleted vertices. Then it's an induced subgraph. Okay? So for the subgraph to be induced, we can still delete vertices, but now we only delete those edges that included the deleted vertices. Okay, now let's see how that works by looking at an example. He says, let's consider those graphs over there. There's 4 graphs, G1, which I'm going to call the mother graph, G2, G3, and G4. All more or less look like that, but there's edges that has been removed. Okay, so let's see how this implicates, or how this fits the definition that we've just looked at. He says both G2 and G3 are subgraphs of G1. Well, what does that mean? It means that the vertex set here is a subset of the vertex set G1 for both of these, and the edge sets are subsets of the vertex, the edge set of G1. Now notice here that it's literally, I'm going to try and cover this with my finger there, then we have G2. Okay? Here we've lost an edge, AB, which was in the initial graph. Okay, so let's see what that means. He says only G2 is an induced graph. Why? Well, every edge in G1 that connects vertices in G2 is also an edge of G2. So this here is an induced subgraph. Why? Again, every edge in G1 that connects vertices in G2 is also an edge in G2. Okay, so it's induced subgraph. In G3, edge AB is in the edge set of graph 1, but not in the edge set of graph 3, or in edge set, of graph 3, even though vertices A and B are vertices in V3. So it's not an induced subgraph, it is merely just a subgraph. Now, what's different about 4? Now let's have a look. If we compare 1 and 4, the edge FC is not an edge in the initial graph. Why not? Well, there was edge FE and EC, but there was no edge FC. So the edge or the vertex E was removed. So let's see what that means. That means that the graph G4 is not a subgraph of G1, even though it looks like it was, but we removed the vertex E. Okay, so the reason is that in E4, the edge CF does not exist in E1. So it can't be a subgraph, because edge 4, E4, the edge set 4, is not a subset of the edge set 1, because that edge set includes the edge FC. Okay, so I hope that sort of helps you to see exactly what he is talking about. So what I'm going to look at now is back to some basic graph theory definitions, and I'm going to give you examples of what each one means. Okay, folks, let us look at some diagrams and some basic definitions. So what are we talking about if we talk about a simple graph in graph theory? Well, an example of a simple graph would be, let's do that. There's 4 vertices, A, B, C, D, and each vertex is connected to another vertex by a single edge. Okay, so A is connected to C, B is connected to D. So that's an example of a simple graph. There are not, so AD is only connected with one edge, not with 2 edges. Each one of these edges connects a vertex with another vertex in the graph. There's no duplication. So that will be an example of a simple graph. Now, if we do the same thing, if we have 4 vertices, A, B, C, D again, A, B, C, and D, and we have AB connected that way and with another path coming back. That's an example of a multi-graph. There's 2 paths between A and B. Then we can go to D, we can do this, we can do exactly what we did before, and have 2 paths between A and D, for instance. The fact that there's two paths there makes it a multigraph. The fact then that we have a loop, we can go from C, tour around and stay in C. That's called a loop. That is part of a multigraph. Simple graphs don't have those things. So they don't have two edges joining two vertices, and they also do not have any loops in the graph itself. Okay, so that is an example of a multigraph. Now, it fits quite nicely with our set theory. A multiset is a set in which we are allowed to include a single element multiple times. Hence the word multigraphs. Okay, so what is a connected or a not connected graph? What do these look like? The graphs that we drew above, there is a connected graph. What makes it connected is that you can get from any vertex A, you can get to C. You can go via D to C, you can go via B to C, or you can go directly to C. Okay? So a graph that is connected means you can get from any vertex in the graph itself to any other vertex on that graph. Let's do 5 vertices. So A, B, C, D, E will be a connected graph. So you can go directly to A or directly to D. And let's do one there, just for the fun of it. Okay, but if there wasn't one here, it means that to get to C, you've got to go via D, or you've got to go via B, or you could have go via A. The graph is still connected. Okay, so when is a graph not connected? Well, if you cannot get from every vertex to every other vertex. So we have a vertex set, let's say A, B, C, and D, and that is a connected graph. But then we have vertex, what can we call this? E, F, and G. And those are connected separately, but there's no way that you can get from F to A, B, C, or D, or E to A, B, C, or D, or G to A, B, C, or D. This is one graph, but it's not a connected graph. So this is important. A graph is not connected can be thought of as two separate graphs where there's no pathway from E to D or G to C. Okay, it's two separate graphs. Then it's not connected. Now these graphs get me excited, the completed graphs. What is a completed graph? A completed graph, let's use 5 vertices again, just to illustrate this. In a completed graph, A, B, C, D, and E, the vertices, in a completed graph, if we add all the possible edges that we can between each of those vertices. So 1 to A, 1 to E, 1 to D, 1 to C. C to B we've got, so C to A, C to D, C to E. We go to D, D to C exists, we need to get to E and we need to get to A. We can already get to B. And then the only edge we need there is the edge AE. That is a complete graph. The graph is connected, okay? So you can get from every edge to any other edge. It is a simple graph because, let's just see, there's only one way from A to C. There's not two paths or loops there. So it's a simple connected graph. It's a complete graph. Between every vertex, there's an edge that connects that vertex to all the other vertices in the graph. Okay, so if every pair of vertices is connected by an edge, we have a complete graph. And they have a name. So this will be K5. The complete graph with 5 vertices. Now, how many edges does that graph have? We'll talk about just now. Since a graph is determined completely by which vertices are adjacent to which other vertices here, there is only one complete graph with a given number of vertices. Okay? And that's it. K5 looks like this. Let's draw K4. K4 will have 4 vertices. I'm not going to label them. And each vertex is connected to every other vertex in the graph. That's what K4 would look like. K3 is simply just a triangle. Okay, that's what that complete graph would look like. Okay, so who's the special name Kn is the complete graph. If I use the notation Kn, it's the complete graph for a graph that has n vertices in that particular graph. Okay, so what else can we say about those graphs, about complete graphs? So we're sticking to complete graphs, and we're going to talk about properties or things that relate to these complete graphs. And just make space here on my table. So, if I talk about the complete graph Kn, what am I talking about? Each vertex in Kn is adjacent to n minus 1 other vertices. So if you have vertex n, it is adjacent to n minus 1 other vertices. Now let's just look at this. This vertex is adjacent to 2 others in K3. In K4, this vertex is adjacent to 3 other vertices in the complete graph K4. If we go to the original K5, sorry, then A will be adjacent to B, adjacent to C, adjacent to D, adjacent to E. So it's adjacent to 4 other vertices. Okay, so that's one of the properties that we have. We call the number of edges now that emanates from a vertex, we call that the degree or the valence of the vertex. So if we look at this, let me use another color, let's use green. Vertex C will have 1, 2, 3, 4, has a degree of 4. We call it a degree or a valence. Okay, so the degree, let's put that here, the degree or the valence of a vertex is the number of edges that emanate from that vertex or node, whatever you want to call it. Okay, so here we have the valence or the degree of that vertex is 3. The degree of this vertex is 2 because there's 2 edges that emanate from that. Okay, so every vertex Kn, in Kn, every vertex in Kn has a degree of n minus 1. Now, this is very interesting, that every vertex will have a degree of 1 less. So if it is 5 vertices, let's see if that is true. There's 5 vertices, each vertex has a degree of 4. There's 4 vertices, each vertex has a degree of 3. There's 3 vertices, each vertex has a degree of 2. Now what does K2 look like? K2 will be there. Each vertex will have a degree of 1. Okay, so that seems to hold for what we're trying to say. So that's fine. But now, how many edges? Edges in Kn, we have that as a question now. One might think that the answer would be, if it is, okay, 4, that it's 4 times 3, because each vertex has a degree of 3. So one will be mistakenly thinking that that's the case. But now the thing that we need to remember here is that every edge is counted twice. Yeah, that edge is counted twice. It's counted in that valence or degree, and it's counted in that degree. This edge is counted in that degree and in this degree. Okay, so every edge has been accounted for twice. So it's not n times n minus 1. The number of vertices, and the number of edges going, or not the number of edges, the degree of the vertex. Okay, so this is not the case. That's not how it is going to happen. Okay, so what does happen here? We can say, because every vertex or every edge is counted twice, we can say, okay, this is indeed the case, but we need to halve it. So how many vertices are there? There's 4 vertices in this case. From each vertex we have 3, a degree of 3 in this complete. Remember, we're talking about complete graphs here. Now that would give us a number 12. If we halve that, it gives us a number of edges, which is 6. So let's count. 1, 2, 3, 4, 5, and 6. Interesting, it works. Let's go to K3. That will have 3 vertices of degree 2 each. We halve it for the number of edges, so 6 over 2 will give us, indeed, the 3 edges. So the number of edges in a graph, one can think about it as the number of vertices. It's a complete graph, by the way, not just any graph. So the number of vertices in the graph multiplied by the degree of each of those vertices. Now, folks, we've seen this in our discrete mathematics before. That resulted in a series of triangular numbers, or a sequence of triangular numbers. Remember that. And everything else. This appears in Pascal's triangle. There's a lot of places where this form takes place. In graph theory, it's only one of them. Okay, so how can we say this differently? In the language that we've learned before, there's n, choose 2. Since we to draw an edge, we must choose 2 vertices. We must choose 2 of n vertices will give me a particular edge. Okay, so that's interesting. That's a few things that we have to remember when we talk about our graphs and how they behave. Okay, so let's try and generalize that last idea that we spoke about when we spoke about complete graphs. How can I find the number of edges in any graph? Okay, now let's build from the complete graph. How did we find the number of edges? Well, we took the valence or the degree of each of those, multiplied it by the number of edges that we had, because that was the regularity in the diagram. Now, graphs that are not complete are different. Okay, so if I have a situation where, let's just draw one. I have this, that, and this. Okay, so let's see, what can we say about a graph that's not complete? Why isn't it complete? Because there's no pathway here. Okay, so this there will have a degree of 2, or a valence of 2. This vertex has a degree 3, that vertex has a degree 3, and that vertex has a degree 2. Now, something interesting that's happening here is that you can see there's two odd valenced nodes or vertices, and there's two even valenced. Now, if I count the number of edges, I get 1, 2, 3, 4, 5. Okay, so how, if I do not know the number of edges, I don't have a graph, and I only have the degree of each of the vertices, how many edges are there in that graph? Well, we take the valence or the degree of each of the vertices and we add them. Okay, we saw there's 5. So if we add that and we divide it by 2, let's see, this is 10 divided by 2, we give 5 edges. Minimum number of edges here that will have the degree of each of the will have 4 vertices with the particular degrees as indicated. Okay, so what do? We just take the degrees of each vertex, we add it, and we halve it. Why does that work? Folks, because between each vertex, this edge is counted twice. It's counted in the valence of that vertex, or the degree of that vertex, and it's counted in the degree of this vertex. So we've included each edge twice. So it makes sense to just halve that answer that we look for. So the sum of the vertices will always be, or the sum of the vertex degrees will always take on that form. So in other words, it will always be an even number. Okay, so how do we find the number of edges? We simply take that and we halve it, and the k will give us the number of edges in this particular case. Okay, let me see where I'm going to next. Next I'm going to go to a handshake lemma that we're going to look at and how it works from there right up to bipartite graphs. So that will follow in the next video. Please remember to like the video and to subscribe to the channel as well.